So to understand about energy flow in systems and in chemical reactions, what we need to talk about, a little review on energy in work. So energy, as you may recall from your wide outside learning, is the capacity to do work. Work is a force acting over distance, F times D. And a force is any push or pull. It's what accelerates an object. So it's mass times acceleration is how you measure force. Now, we're not going to work directly with those physics equations, but that's the background that we're talking about here. Energy, which is that capacity to move something a distance, speed it up as we move it, is measured in joules or calories. Traditionally, a calorie was the first measurement of heat energy, and it's the amount of energy it takes to raise 1 gram of water 1 degree Celsius. In joules, that corresponds to 4.18 joules, and joules is the metric unit that we will be using here. So you may recall that when we talk about energy, there are two very broad categories, kinetic and potential. Kinetic energy is the energy of motion, so mechanical energy, the vibration of particles, anything that has to do with things moving, an object actually moving somewhere, that is kinetic energy. Potential energy is the energy that's stored in a system. So we talk about positional energy, an object that's being pulled by gravity but isn't free to fall at this moment in time. And yet when it becomes free to fall, the energy will go from potential to kinetic. For our purposes, we're really concerned about the energy that's stored in the bonds between atoms, in molecules, and in ionic compounds. That there's an amount of energy that's released when they come together to become more stable, and there's energy that needs to go in to break them apart. And moving that energy around is what we're going to look at. So at the quantum level, it's important to understand, as Albert Einstein once taught us, that energy and mass have a correlation, have an equivalently. They're basically two sides of the same coin. E equals mc squared. So the net total of all the energy and all the matter in the universe can never change. What that means is both matter is conserved. So in a normal chemical change, there is no magic where stuff appears or disappears out of nowhere. And at the quantum level, matter can become energy, energy can become matter. But what's true also is in any system, the change in energy from beginning to end, there's no net increase or decrease in energy. The energy may flow from one part of a system or from the system to the surroundings and from the surroundings to the system, but it never is created or destroys. It just changes its form in the universe. Okay, so it's conserved. That's the first law of thermodynamics. So when we talk about heat and temperature, a word about this. So temperature is a measure of the average kinetic energy of the particles. So we've talked about before when we're looking at gases about a Boltzmann distribution, that there are some particles that are moving slower than all the others, some moving much faster. And if we look at an average distribution, the temperature is where most of the particles fall. These were originally, the temperature scales that we use were originally derived based on the physical properties of certain things. So Celsius, for example, figured out his scale by taking a column, a narrow column with alcohol in it, dipping it in ice, putting a mark, and then slowly heating that up, and then bringing that water to a boil and putting another mark. And so based on the phase changes of water, and put 100 marks in between, that's where he came up with his scale based on water. The Kelvin scale, William Thomson, Lord Kelvin, doing some math and extrapolating back the behavior as you cool things, figured out there's a point at which you can't get anything colder, and that's negative 273.15 degrees Celsius. We call that absolute zero. On a particle level, we understand that as a state where the particles have no kinetic energy, where kinetic energy equals zero. In a later presentation, we'll talk about that being the third law of thermodynamics. When we talk about heat, while we kind of measure temperature, which is vibrational energy of particles, heat is really the movement of energy from one system to another, from one sample of matter to another, from system to surroundings, the things next to it. And they have to be at different temperatures. Ultimately in the universe, everything wants to get to equilibrium. So energy spreads out. Again, later we'll talk about the idea of entropy, everything goes to randomness. But for now, just understand, heat is the transfer of energy between things that have different temperatures, okay? So it's kind of amorphous, but we're going to talk about it as if it were a something, almost as a material thing in a reaction for our purposes. But really it is the transfer. So the heat energy in one thing, or the kinetic energy of one thing, influencing the kinetic energy of the thing next to it that it's touching. So when we talk about energy flow, we have to talk about which way is it coming? Is it coming into a system or leaving a system? So we use two terms, exothermic and endothermic. Remember, exo, like an exit, to leave, and endo is an inside. You and I have an endoskeleton. Well, in this purpose, when we talk about endothermic reaction, we're talking about heat moving into the system or into the reaction. So exothermic is where energy flows from the system to the surroundings. So if you look, we start with some reactants. We have to put some energy in. We have to get the ball rolling. We'll talk about that later. It's called activation energy. But once that reaction happens, we end up with products that have less energy in them than what we started with. And so the heat comes out. Okay? The heat comes out. So these things feel hot. Exothermic reactions feel hot because we're in the surroundings. What's happening in the system is energy is coming out, and where's it? It's got to go somewhere. Can't disappear. So we feel it. The opposite is true of endothermic. We start with things that have less energy, and we have to put a whole bunch of energy in to make this happen. And once it happens, we end up with products that the energy that have greater potential energy inside of them. And in this case, the heat's going from us, from the surroundings, into the system. So these are things that feel cold. So we measure the change in the surroundings and say, well, are the surroundings getting hotter? Then this is an exothermic reaction. Are the surroundings getting colder? Then this is an endothermic reaction. So let's talk a little bit about the Zen of Thermo. The Zen of Thermo seems like an odd idea, doesn't it? Well, stay with me. Energy transformations are a state function, which means that we care about the state they're in. We don't care how they got there. It doesn't matter the path, only where they are right now, where they were at the beginning of a process and where they are at the end of a process. Okay? Only the state of the system at any present moment matters, rather Zen thought. So how you get from the beginning to the end of an energy change, it doesn't really matter, because there could be a million different paths to take, but they all in the end result in the same amount of energy transfer, either into or out of a system. So only the isness, the current state, what it is now compared to what it was before the reaction happened or before the process happened. That's all we care about, is where did we end up? How is it different now from before? Not how did it get there, by what path did it get there. There could be 4 or 5 different possible mechanisms, possible explanations, a whole bunch of input of energy and release of energy, but at the end of the day, we either ended up with a certain amount more energy in the system or a certain amount less energy in the system, and it doesn't matter which way you get there, okay? So it is what it is. The change is the change. So let's talk then about heat capacity. When we talk about the movement of energy, we've got to measure it. We've got to take the temperature of things to see how the temperature changes. But temperature is one thing, the average kinetic energy of the particles. Heat is the transfer of energy, and that transfer of energy also has to deal with the energy between particles. And so just because we put energy into a system doesn't mean that we're going to see the temperature change right away, that the average kinetic energy of all the particles will be different right away. We call that sort of lag heat capacity. So every substance has a certain holding capacity for heat. And that's because of the inertia of the particles that are there and the interparticulate forces, the intermolecular forces, if we're talking about a molecular substance, or the ionic attractions between positives and negatives, or even the London dispersion forces between nonpolar materials. But whatever the forces are holding them there, when you put energy in to try and get particles to move in a different way, you have to overcome some of those other potential energies that are in the system. And so we put energy in, we don't necessarily see an immediate or direct temperature change. And the amount of energy we put in is not exactly linear to the temperature change we see. There's always at least a lag because we have this thing called heat capacity. So the addition of kinetic energy to the particles does not directly correlate to a change in temperature, at least not instantaneously. You have to overcome some of those other forces at work. Particles resistant to move, inertia we call that on the physics level, or the intermolecular forces and interparticulate forces that are kind of holding everything or keeping everything from moving more freely than they are. Right, so the amount of energy needed to raise the temperature of a sample is called its heat capacity. And depending on what you have, everything has a different heat capacity. And in order to standardize it, let's talk about the same quantity of substance. So if we compare 1 gram of any substance to 1 gram of any other substance, see how much energy it takes to raise the temperature 1 degree, we call it specific heat capacity. And that's the value that we're going to be very concerned with as we go through this unit on calorimetry and thermochemistry. So just so I have a sense, here's a specific heat of some materials. This is a handy little reference for you. I do have an activity I'm going to ask you to do where you're going to see if you can't derive some of these and look at the change experimentally, the change of those things. So the other thing we have to remember is pressure. Okay? With gases, changes in pressure causes change in temperature, and change in temperature changes cause in pressure. Right? This is how your car engine runs. We heat a gas and it expands. So we heat it, and then it exerts pressure, which moves a piston, which turns the crankshaft, which turns the wheels in your car. So we have to account for pressure because pressure can change the temperature of gaseous particles, all right, of a sample of a gas. So how they're moving around is a function of how much pressure that there is in the container that they're in. So we have to level that out. We have to take that variable out for us to really look at the energy transfer of just what's happening in a reaction or a process such as melting or boiling, or solution, one thing dissolving in another, where there's an energy change in the energy state of things. Okay, so for us just to focus on the heat of the process, the system has to remain under constant pressure. Okay? And when we talk about the heat transfer or the energy change of a system under constant pressure, the term for that is enthalpy, and the shorthand for that is delta H. So enthalpy is what we're going to concern ourselves with. So to measure enthalpy, we use a device called a calorimeter. So here's a fancy bomb calorimeter. This is how food analysis is often done, where you have a chamber, a two-chambered system. One chamber has your sample in it that you end up combusting, usually using electricity, and it sits inside another chamber that's filled with water. If we measure the temperature of the water, we know how much energy has either come out of or gone into the system. Now, again, if we're analyzing energy content of food, which is what this particular device would do, it's always going to heat the water, right? So energy content is often measured with a thing called a calorimeter. So the heat transferred either from or to the materials in the reaction chamber changes the temperature of the water. And the assumption is that the materials of the walls of the chamber have a very low heat capacity, so that we don't have to correct for it, or it becomes negligible for us. So what happens in the temperature of the surroundings, in this case the water, tells us what happened inside the system, like what's inside the sample cup. So if we use a device like that, or a more simple system like just 2 coffee cups, and if we're combining things that will release heat as a reaction, and we look at the water that is the medium, again, a temperature change in the water tells us how the particles have changed their energy states, become more or less stable, absorbed energy, released energy. So here's our little formula. Delta H, enthalpy, is equal to the mass times the specific heat times the change in temperature, where the change in temperature is the difference between where you ended up and where you started. And for this calculation, we're concerning ourselves with degrees Celsius. Okay? Our table values for specific heat in Kelvin, and if that became an issue, we could do that, but for the most part, we're concerning ourselves with degrees Celsius. So heat exchange is measured by the change in the surroundings, just like in that bomb calorimeter in the last slide. It's what happens in the water tells us what happens in the chamber. Okay, so if we put a candy bar into that chamber and we burnt it up, and the outside chamber, the water, there were 500 grams of water, and the temperature changed by 40 degrees Celsius. That would translate into 20 calories with a capital C. Food calories actually kilocalories, so kcals. So small calories, the temperature, the energy it takes to raise the temperature of water. 1 gram of water, 1 degree Celsius. That's a tiny amount. In our food, it's the amount of energy needed to raise 1 kilogram of water, 1 degree Celsius, or 1,000 grams of water. So it's 1,000 times the energy. So 20 calories on the food label is actually kilocalories. So that would translate into 83.6 kilojoules of energy. So we put it in the chamber, we combust it, it burns, it gives off heat. The water gets warmer because it absorbs the heat energy. What's left in the original reaction chamber has less energy. So we've made an exothermic process happen. Okay? So whenever there's a positive change in the system, that means the surrounding temperature goes down. The enthalpy is a negative value. And whenever the system releases heat energy, so the temperature, if you will, of the particles, the average kinetic energy of the particles goes down, then that energy is transferred to the particles in the surroundings, and so the energy of the surroundings goes up. So whenever we calculate, we're usually calculating the surroundings, which tells us with the opposite sign what happened in the system itself. And that's an important thing to keep straight as we go forward and as we practice these.